we tried to develop K matrix from physical sense, that is equilibrium, for truss structure. Using the same concept, what we did was, for a given inclined beam, inclined link member, we derived element stiffness matrix. So let me show you what I have done previous class. So let's say this is a two-dimensional structure, this y-axis and x-axis, this has node I and this has node j. We know that our DOFs are ui in the x direction and vi in for the ith node, similarly uj and vj. The corresponding force field or the force conjugates for that one is pj, qj. These are the forces. Similarly pi, qi. So what we did was we tried to disturb this node I, keeping the node j constant with with ui, and vi, uj, vj all are kept constant, and then we showed that the stiffness of this is k, which is equals to ae by the length. Length is nothing but xi minus xj whole square plus yi minus yj whole square under root. So anyway, that we know. So we want to show that it is equals to ae by l cos square. So let me just write those things from the previous class. We said it is equals to cs minus c square, yes, sorry, minus cs times ui is equals to pi, qi, pj, qj, provided only ui is disturbed, or the degree of freedom 1 is disturbed for this one. So where our length is defined by, our length square is defined as xi minus xj whole square plus yi minus yj whole square, and our theta, which is defined as this angle theta, is defined as, or cosine of theta, which I call it as simply c, is equals to xj minus xi divided by L. Similarly, sine, which I define it as S, is given by yj minus yi divided by L. And based on this, I can also apply a unit Vi and see what are the force fields to keep it under the equilibrium. Similarly, for Uj, keeping all other things 0. Similarly, Vj and keeping all other things 0. One can develop the entire stiffness matrix for the all 4 degrees of freedom, which will be written as c square cs minus c square minus cs. Because it is symmetric, one can easily write it in this manner: s square minus cs minus s square minus cs minus s square plus c square plus cs plus c plus s square times ui vi uj vj, and this is the sum of forces from all the contributions. So this is pi, not just ui here, but ui vi uj vj, all the sums. So qi vj qj, this is what we have shown, and we showed that this is nothing but, this entire quantity is nothing but your stiffness matrix for the element E, with this as element degrees of freedom, and this is your force field on the elements. Okay, so Ku is equals to F form, and U for this given element, which is an inclined element, it's an inclined element Ij, and this theta is quite arbitrary, so, or generic in nature. So this is applicable for any inclined member. So with this, so your ui, vi, uj, vj represents the global coordinate system, and vi, qi, pj, qj represents the global forces. These are global degrees of freedom, global forces, and depending upon the inclination, the coefficient would change in this manner, with ae by l as being its longitudinal stiffness. So this is the element stiffness matrix. So that is what we have developed in the previous class. Now, in today's class, we also have to know how load is obtained. Load is nothing but how this matrix has been generated. We are focusing on this one a priori. Now, given the self weight and other things, point loads, how this pi, qi and other things has to be obtained, that we'll be seeing in today's class. And once that is there, we'll try to look into a simpler example. Okay, so now let's start with first one is under the thing self weight. Self weight is because of the gravity. Let's say you have an inclined member, and you have some weight acting on it, because the member has a self weight which will be uniformly acting on it. Uniformly in the pi direction. So let's say it is small w, and into length will give you the capital W. So capital W is equals to, let's say, small w into L. So this is approximated in our case as it is equally distributed onto the nodes, and hence it would become W by 2. So we can write, because of this, as our load due to gravity or self weight is written as due to gravity or self weight or body load, whatever you want to call it as, x direction. So both are 0. So pi, this is I and this is j. At I and j, there is no, now coming to the vertical load, it is in the negative direction. So this is minus w by 2. This is again horizontal load at the q is j is 0, and the vertical load at the j is w by 2. this is due to the point load. Let's say if we have, this is the first part, you can also have because of the thermal expansion. Let's say because of the thermal expansion, you will have, um, let's say in a longitudinal member, because of the alpha AT would be, sorry, alpha delta T would be your strain, and then your stress would be with A, and your forces would be with A. Or so E alpha A delta T, whatever you want to write it as, let's put it as delta T. So these are the stresses in the member, which would be split into, for an inclined member, as force field because of thermal expansion is of minus C minus S plus C plus S E alpha A T, or generally it is delta T, whatever you want to write as delta T. Delta T is increasing the temperature from the reference temperature. So this is due to the thermal expansion. Similarly, we want to see that because of the equilibrium, K into K element into your U, or the degree of freedom, is equals to R. So I'll be interchangeably using U and R for these things. So this is your same as U and this is the same as R. So your internal forces is equals to the external forces. So, but we know that the elemental forces Re comes because of the R due to gravity, or F due to gravity, plus F due to thermal. Okay, so we can get it because of both. um, in generally interest members, the expansion would be there, so we need to consider thermal expansions as well as the gravity that will give us the elemental forces. But we know that for any given R, because of Newton's third law, R bar, for every action you have reaction, so R bar is equals to minus R. Okay, so this would be the thing. Now when I take total force balance for a truss member, it is external load plus internal load, all acting must be equal to 0. Okay, so the internal load comes from the external, let's say the external load is the applied load capital P, and the internal load is because of the resistance and the structural loads. Okay, so that means we know that P plus Re is equals to minus R, which is nothing but our R bar, right? So this is your externally applied load. This is load due to body, and this is your resistance. So, and this is equals to K times, because minus would be given in the as above. So your K element times D is equals to the external load plus the loads on the elements due to things. So this is your total force that will be acting on this. This is your degree of freedom, and this is your stiffness of the structure. We showed that this is what you are applying as at the nodal load forces that may be like for a truss gutter bridge. The load of the vehicle is put onto the nodal things in some proportion of their respective spans. That is the external applied load, and RE would be the body force itself, weight, as well as the temperature changes that brings about the changes. So this is your force field, and this is your stiffness, and this is your degree of freedom. But this is for single element. So for an inclined member, but we want for a given full truss, we need to stiffness matrix. So in the second part of today, we will go with an example. This is example. Let's choose some example, whichever is will help us try to educate to solve this problem. So I will take the same example what I've been solving it earlier. This is like a simply supported truss. This is on a roller support. This is pin support. This is roller support. Let's say it's been loaded with some forces P on the top face, and let's say each one has a stiffness of A and E, cross section and Young's modulus as AE. So A and E, A and E, A and E. Let's assume each is 60 degrees. So the length is also same for all the members. And we are solving this problem. So we want to solve this problem. We want you the deflection of each points as find out the reaction forces due to application of the following forces. The stiffness of each of the member is same. So since all has same length, and the thing k small k can be defined as AE by L. Is that? So let's let's solve this problem. Let's try to obtain nodal deflection of all the joints. That is our thing. So let's try to solve this in a finite element sense. So let me redraw it. So let me take this. So Let us number the nodes first. So let me take this as node 1, node 2, node 3, node 4, and node 5. And let us name the elements as element 1, element 2, element 3, element 4, element 5, element 6, element 7. Let's write the connectivity table. Element number of the element 1, node A, node I, node I, and node J. And let me write it a little bit closely. Node I and node J, and let me also kind of find out my theta. Anyway, the length of all the things is same because theta is 60. I maintain 60. It's an equilateral triangle. So in an equilateral triangle, all the length of the members are same. So then same for all the members. So still, let me make the entries. So the element, we have 7 elements. 1, 2, 3, 4, 5, 6, and 7. For the first element, the nodes are node 1, node 2, and the angle it makes with respect to horizontal is 0 degrees. Next one is second element. It has node 2, node 3, and its theta is 0. Next one is this one 3, which is has 3 and 4. The angle it makes with respect to that is 20 degrees, right? So this is 90, this is 60, so it would be 120 degrees in terms of degrees. So, and for the fourth element, again it is 4 and 5. The thing that it makes from I to J, because this is I and this is J, it makes 180 degrees. So let me put it as 180 degrees. Next, if I come to the node 5, it has, sorry, element 5, it has node 5 and node 1. The angle it makes is, this is 60 and this is 60. I can make it as minus 120 degrees. Okay, and the sixth element, it has the node 5 is minus 60 degrees with the horizontal. This is because this is I and this is J. Ij from the horizontal is minus 60, whereas for the element 5, this is I and this is J. This angle would be 120, minus 120 degrees. Similarly, for the element 7, if I pick my node I as this one and node J as that one, then it will be 2 and 4. And for the 2 and 4, since the angle is 60 degrees, so this would come to be 60 degrees. Okay, so this is what we have first seen, and based on that we will try to develop the element stiffness matrix for each and every element. So let me just take this thing again here. So since I have taken this, I'll be getting for a give this as my given structure. This is my 1, 2, 3, 4, 5, and my elements are 1, 2 is an element, 2, 3 is the second element, 3, 4 is the third element, fourth element is 4, 5, fifth element is 5, 6, sixth element is 5, 2, and seventh element is 2, 4. So this is what is node I and node J. Correspondingly, my theta ij is what I have written as per this. So then what I will do is, so let me just so let me write my C. Let me write my C and S correspondingly for this. So the cos 0 is 1 and the sine 0 is 0. This is any problematic, right? So however, when you look at this fellow, this is minus 1 and this is 0. Now coming back to sine, cosine, this would be root 3 by 2 and cosine would be minus 1 by 2. Okay, so and similarly, so this would be this is minus 1 by 2 and this is minus root 3 by 2 and this one is again sine 60. 60 would be and 1 by 2 and this one is 1 over 2 and root 3 by 2. So with this as my cosine and sines for corresponding thing, the element stiffness matrix for the first element, I can write it as K for the element 1 or for generic element is given as AE by L, which is nothing but small k times it is C square CS minus C square minus CS. This is CS minus plus S square minus CS minus S square minus C square minus CS plus C square plus CS minus CS minus S square plus CS plus C square is the K matrix. So correspondingly for the element 1 I can write it as, so I'll try to move this here. So this is the element stiffness matrix. So using this I can write for the element 1, since I know everything so perfectly, my C's and S are depend on the theta, which is cos theta and sin theta. Correspondingly, I can write this as small k times 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0 plus 1 0 0. This is for the first element. Now when I come to the element 2, k of an element 2, this is also very similar. There is no difference because my length is same, my AE is same, this is same. So I would write this as the same as element 2. Let me not rewrite it. It would be, and since the theta is also same, it would be same as the element 1. My K2 is same as element 1. Now let me come back to the element 3. For the element 3, let me write it. K for element 3 is written as small k times my C is minus 1 by 2. So C square would be 1 by 4 and CS would be root 1 by 4 and plus minus root 3 by 4. Similarly, this is equals to root 3 by 4 minus 1 by 4 and minus root 3 by 4. And let me take 4 common, so it would be coming same, so that we can get rid of the things. So let me write it as by 4 as common. This would be 1. This is minus root 3. This is minus 1 and plus root 3. Next one is minus root 3. Sine square would be root 3 times root 3. 4 is already taken. This is 3 and the next one is plus root 3 and this is minus 3. Similarly, this is minus 1 in CS. This would be plus root 3. This is plus 1 minus root 3. Next one, this is root 3. This one is minus root 3 and this one is plus 3. I just derived based on this as C and this as yes. Similarly, let me just copy it again. Or let me just move these things little bit so that I can have a view of it. So similarly, let me write K4 K for the element 4 is anyway. Let me do the fourth one. So this is minus 1 and 0, so things remains more or less same. This is 1 0 minus 1 0 0 0 0 0 because anywhere s appears, it is 0, and c always comes here as c square, so it should not change it. This is again same as minus 1 0 0, sorry, 1 0 0 0 0 0. So this is k4. Now let me come to the k for the element 5. The k for the element 5 is given as, now c is minus half and this is minus root 3 by 2. So in this case, this again, let me sorry about that, there's a small k missing here. So small k by 4 will be still there here, and c square would be 1, cs would be root 3 minus 1 minus root 3, root 3 minus 1, just by symmetry I'm writing it, minus root 3. Okay, similarly s square is, this is minus root 3 into minus root 3 would be positive, so this would become minus root 3 and minus 3. So by symmetry I can again write thing as this one as this. Then by symmetry I know if it is minus 1, this would be plus 1 and this would be plus root 3, and if this is 1 and minus 1, this would be root 3. Anyway, I can tell it in this manner also. This would be the k for the fifth element. Similarly, let's do the k for the sixth element, which is equals to small k by 4 times, again let's have a look at it. This is for the sixth element, this is 1 and this is minus root 3, so this would become 1 and this is minus root 3 and this is 1 plus root 3. This is minus root 3 by symmetry, sorry, this is minus 1, this is minus 1, this plus root 3, and sine square is 3 and this would be plus root 3 minus 3. Again by symmetry, this is plus root 3 and this is 3 and minus 3 by symmetry, and this would be plus 1 and minus root 3, and this would be again minus root 3 by symmetry, this is 3 by symmetry. So this is my k6. So this is how I have derived k1 through k6. Similarly, I can show my k7. Let me just derive it in a minute. So let me just derive my k7. So my k for the element 7 is given by looking at this one. C is 1 and S is root 3 by 2, 1 by 2, and C is 1 by 2 and S is root 3 by 2. I can rewrite this thing as small k by 4, 1 root 3 minus 1 minus root 3 minus 1 minus root 3. This would be 3 minus root 3. This is minus 3. This is minus root 3. This is minus 3. This is plus 1 minus 3. This is, sorry, I made a mistake somewhere. This is plus root 3 and this one is plus root 3, and this one is plus 3. This is my element stiffness matrix for the 7th element. So to make the completion, so let me just state like this. My is this one, and my K2 is same, so I can write this as K2, K1 and K2 are same, and my K3 this is my K1, this is K2, this is K3, K4, K5, K6, and we have K7. Okay, so but let us have a view that what does each degree of freedom represent. So for the element stiffness matrix, the I and J corresponds to, these are the degrees of freedom. So let me write my degrees of freedom. Let me go back and write my degrees of freedom. So the degrees of freedom is U1 V1, U2 V2, U3 V3, U4 V4, U5 V5. Since there are 5 nodes, there are 10 degrees of freedom. Let me number the degree of freedom. The number for the U1 is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, and this is 10. There are 10 degrees of freedom. So for the first one, this row is corresponding to U1, this is corresponding to V1, this is U2, this is V2. Similarly, these columns are, similarly I can write this row corresponds to U1, this is V1, this is, and this is U2, V2, U3, V3, U2, V2, U3, V3. For the third one, this is between 3 and 4. So for the third one, it is U3, V3, U4, V4, U3, V3, U4, V4. For the fourth one, it is corresponding to U4, V4, U5, V5. So it is U5, sorry, U4, V4, U5, V5. For this fifth one, it is 5 and 2. For the fifth element, it is 5 and 1. Fifth element. So it is 5 and 1 will make U5, V5, U1, and V1. Similarly, this row is corresponding to U5, this row is corresponding to V5, this row is corresponding to U1, this row is corresponding to V1. Correspondingly, for this one, it is U5, V5, U2, V2, U5, V5, U2, V2, and correspondingly for the seventh one is between 2 and 4. So this is U2, V2, U4, V4, U2, V2, U4, and V4. So what are the degrees of freedom? The degree of freedom is numbered as, let me also number them. So the either you can have it in this method or you can number the degree of freedom. This is 1, this is degree of freedom 2, this is degree of freedom 3, this is 4. So this is 1, 2, 3, 4, 2, 3, 4, 5, 6, 3, 4, 5, 6. This is 3. So this is 5, 6, 7. Just a minute, I might have made a mistake. This is not U5, this is V4. So that means this is 7 and 8. So 5, 6, 7, 8. Similarly, here would be, this is 3, 4, this is 7, 8, 3, 4, 7, 8. So this one would be 9, 10, 1, and 2. So this is 9, 10, 1, and 2 degree of freedom. This would be 7, 8, 9, 10. 7, 8, 9, and 10 degree of freedom. This would be 9, 10, 3, 4, 9, 10, 3, and 4th degree of freedom. So accordingly we identified everything. So now I want to write a global stiffness matrix. The global stiffness matrix would be something like this. K global is equals to, with respect to, what are the degrees of freedom? The degrees of freedom is first degrees of freedom, second degree of freedom, third degree of freedom. Let me write it a little spaciously. 1, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th degrees of freedom. Similarly, it is first entry, second entry, third degree of freedom entries, fourth degree of freedom entries, fifth degree of freedom entries, sixth degree of freedom, seventh, 8, 9, and 10. So just a minute, I'm getting a call. Hello. Yes. I'll talk to you later. I'm in a class. So anyway, let's get back to the thing. Now let's see the first. Anyway, what are the degrees of freedom? I want to rewrite it in terms of actual quantities. This is U1. This is 1 means U1. Even numbers are U's. This is U3. This is U4. this is u5. We have 5 degrees of freedoms. So this is u displacement. Similarly, odd numbers, sorry, even odd numbers are u's, even numbers are for the v's. So corresponding to those entries, we need to fill it up and try to write the solution. So let me just unzoom it, and so that we can easily write it in one go. So let us see how we can write it. What is the entry in the 1 and 1? u1 and u1, the entry is small k. So let me take the entry of the small k coming from this place. u1 and u1 is a small k. And is there any again u1 and u1 in this second element? No, there is no u1 and u1. And in the third element, there is nothing. In the fourth element, no, there is only u4, u5. And in the fifth element, there is again a u1 and u1 entry, which is equals to minus k by 4. Okay, so let me try to write it smaller because I may lose space. The entry coming from the previous thing is k, and the one that is coming from here is k by 4. And is there any other things? No, because the first u1 is connected to only two elements. That is, its stiffness comes from the element 1 stiffness matrix and comes from the fifth element stiffness matrix. That's the reason only we have found in the first element u1 entry and in the fifth element u1 entry. So similarly, we can do for the u1 v1, there is anywhere 0, so this one is not a problem. Then let us say u1 in the row, sorry, this u1 I think we should have written this one as plus, because this is the u1 and u1 is this the positive one, not this one. So u1 and u1 is this one. So it is 1 into k by 4, it is k by 4. So let me rewrite it clearly. So u1 and u1 coming from the first element stiffness matrix, this is small k, and from the fifth element coming from u1, and u1 is 1 times k by 4, so this is plus k by 4. So let me take k outside from all the things, so that makes my life easier. So let me put small k out. So this is 1 plus 1 by 4. This would be, I will take 4 also outside common, so then it makes my life even more easier. So this will become 4 plus 1, and this one will become, um, this one is u1 times v1, this is root 3. There are also no temperature variation, so assume weightless and no temperature variation. In that case, the force field coming from the gravity is 0, and the force field coming from the temperature is also 0. I don't have to worry about it. Only the external forces I need to worry about. Let's see the external forces. So the external forces in this given structure are acting on the 10th and 8th degree of freedom, right? In the negative direction with the p thing. So that means my q phi is minus p, and my q8, sorry, my q phi I have here, or to rewrite it, I can say that my q phi is equals to minus p, and q4 is equals to minus p. Other than that, all the p and q's are zeros. So let me rewrite it. My external forces are all zeros. This is external forces. This is p1, q1, p2, q2, p3, q3, p4, q4, p5, q5 can be written as, we know that except p4 and sorry, q4 and q5 all are 0. I can keep writing p1, p2, p3, sorry, p1, q1, p2, q2, p3, q3 are 0, p4 is also 0, q4 is minus 5, p5 is 0, q5 is minus p. So p1, p1, q1, p2, q2, p3, q3, p4 minus q4, p4, q4, p5, q5. So this is what we have already written, except q4. This is q4 and q5. All other things are 0, and these values are equals to minus p. Now I'm ready to solve this matrix. So my total load, total force V is equals to, due to the external force, external plus gravity plus temperature. So anyway, this is zeros because there is no temperature variation. There is no gravity here in my case in the current problem. So that is no self weight is there. So if there is no self weight, the gravity forces are 0. Only external forces are there. So my force field F is nothing but only due to the 3 0 minus p, 0 minus p. This is the only my force vector. So I know my, so now I have the forces. So I can write my k global times my d vector is equals to my force vector. I know my force vector is obtained by this. My d vector is degree of freedom 1, degree of freedom 2, so on, degree of freedom 10, which is nothing but u1 v1, u2 v2, so on, u5 v5 in this case. Now still this K matrix is singular. You cannot invert this directly because the structure is not stable. Why the structure is not stable? Why? Because we didn't impose the boundary condition. Why the boundary condition has to be imposed? The boundary conditions are required to make it means to make the structure statically stable. Statically stable means arrest all kinds of rigid body motion. So what are the rigid body motions this can have? It can have translation along x, it can have translation along y, and it can have rotation about the z axis. So in order to constrain that, our structure has been already constrained. So let us see our constraints for the given problem. The constraint for this by the rigid body degrees of freedom, because this is a pin supported, the things u1 is already 0. Because this is also a pin support, v1 is also 0. At the same time, since this is a roller support and the vertical displacement is constrained and the horizontal is still unrestricted, the v3 is equals to 0. By constraining these u10, v10 and v3, this will arrest x degree of freedom, this will arrest the y degree of freedom, or rigid body along y direction. Together these two will provide the rotation is also constrained for this given problem, rigid body rotation. So these three helps us to make the structure stable. That means my actual unknowns for the problems are my D matrix is u1 v1, u2 v2, u3 v3, u4 v4, u5 v5, out of which I know that this is 0, this is 0, and v3 is also 0, and all other things are unknown. So my u unknowns or degrees of freedom unknowns are nothing but u2, v2, u3, u4, v4, u5, and v5. So now if I want to solve the problem, I need to get KUU. To get the KUU, or to solve the problem, I just need this. So in order to do that, you go to the force vector, you eliminate anything with respect to u1, with respect to v1, and with respect to v3, that is u2, v2, u3, v3. So the remaining thing would be your fu. So the fu for this problem is given by 1, 2, 3 zeros, and then another 0 minus p, 0 and minus p. Okay, so 1, 2, 3, 4, 5, 6, 7. So 7 is right. This is your fu. Similarly, the KUU is obtained by eliminating the row with respect to u1. Let me eliminate it. This row, eliminate the u1 row, I don't need it. Similarly, v1 row is also not required for me, and I also don't need the row with respect to v3, that is the sixth degree of freedom is also not required. Similarly, I need to eliminate is eliminated, v1 is eliminated, and v3 is eliminated. So anything that remains in between will give you my KUU. So this thing remaining is your KUU. So just rewrite it by taking this one as n. This is 0, minus 4, minus 1, minus root 3, minus 1, plus root 3. This is 0, 6, minus root 3, minus 3, plus root 3, minus 3, minus 4, plus 5, plus 3, root 3, minus 4, then minus 1, minus root 3, minus 1, minus 3, minus root 3, 4, minus root 3, minus 3, minus root 3, 3, 0, 0, minus 1 root 3, 0, 0, 0, 2, 0, root 3, minus 3, 0, 6 would be your KUU. So let me not rewrite it, I will just leave it. KUU is obtained by eliminating first, second, and sixth rows and column. So V1, this corresponds to V3. So once you get this, then you obtain 3 U4, V4, U5, V5 as inversion of KUU times the force U. We already showed what is FU. We know KUU now. If you try to invert it and do this multiplication, you'll end up with the degrees of freedom. So in this manner, you'll obtain this thing. Once you have obtained these things, you try to put this back into them times F. Whatever the remaining things after crossing the thing, that will give you your reaction to the horizontal. This is the stiffness matrix. Once we have the stiffness matrix, we can handle any truss problem. So for that, we have taken this example. In this example, we have like 7 members and each member is having different inclination. So first we created an element connectivity table for the problem under the consideration. So for this is the nodal connectivity. There are 7 elements. Each element has corresponding I and j's that will determine its inclination with respect to horizontal. We have these kinds of inclination. And then we found what is its cos theta and sin theta and tabulated it. And using this cos and sin thetas for the corresponding elements, and we know this element stiffness matrix, which is nothing but A by times this cos and cosine form. What we did is we have written the element stiffness matrix for the element 1, element 2, element 3, 4, 5, 6 and 7 because we have 7 elements. And we know that in the global scenario, we number the degrees of freedom as 1, 2, 3, 4, 5, 6. The 1 will correspond to x degree of freedom and y is correspond the odd number corresponds to y degree of freedom, that is u1 v1 u2 v2 u3 v3 u4 v4 u5 v5. Since we have 5 nodes, 5 x displacements, 5 y displacements of the nodes, that is u1 v1, all these things. Either you can call it as u1 v1 u2 v2 or you can call it as degree of freedom d1 d2 d3 d4 d5 d6 d7 d8 and d9 d10. So correspondingly, we have earmarked it. What is the stiffness of the nodes are also corresponding to elements. So for example, for the first element, the connectivity is between the degree of freedom 1, 2, 3 and 4. So we have marked the columns as 1, 2, 3, 4 and 1, 2, 3, 4. So this corresponds to the stiffness of 1 and 1 degree of freedom. And this one corresponds to 1 degree of freedom and the second degree of freedom, 1 and 2. So similar to this, once we have earmarked this, we can construct our global stiffness matrix, because now in the global stiffness matrix, we should have all degrees of freedom. The total degrees of freedom in this problem are 10. So we earmark all the things as 10 degrees of freedom along the columns as well as along the rows. Or if you don't want to call it as 1, 2, 3, 4 degrees of freedom, you want to have physical meaning, 1 corresponds to U1, 2 corresponds to V1, U2, V2, similarly, so on. So you have those things, and we bring each and every local stiffness matrix and dump it into the global stiffness matrix by matching the address location. 1 and 1, 2 and 2, all these things should correspondingly come and sit in the same places. And because of that, at some places the stiffness will add up, because for that, what happens, several members come and sit at one place. For example, If you look at this place, you have stiffness coming from this element, you have stiffness coming from this element, you have coming from this element, you have stiffness coming from this element. So for these degrees of freedom, you have at least 4 entries at these places. So that's the reason you can see at some places you have as much as 4 entries coming from different things. Similarly, at some places you have 3 elements. This is one element, second element, third element. So at some places you have 3 entries possibly. And if it is a 0 entry, I haven't added it. So, and at most you have single entry, or if there is no entry which corresponds to 0, I haven't entered. Once we have assembled the structure, we also have to find out the force fields. But the force fields comes from the gravity. Correspondingly, in this places, since I have ignored the gravity, I have made my gravity forces 0, and I have also assumed there are no temperature variation. I'm only solving the problem under the external loads, and the external loads are 2-point loads acting vertically at the 4th and 5th nodes. Correspondingly, my Q4 is minus P and Q5 is minus P. Because of this, I would have this P. And if you want to consider the self weight and the temperature variation, I would suggest that we have discussed earlier how to handle the gravity forces and the temperature forces. Gravity forces are the weight consideration you have equally distributed under the each nodes connected to it, and alpha the temperature variation follows minus C minus S, C and S into E alpha delta T, which we have discussed earlier. That can also be added, but since current problem doesn't have that, I have ignored it. And then I've just added my total force is nothing but external forces, gravity forces and temperature, which are ignored because of 0. This is my thing, this is my total external forces acting, and that will become my total force also acting on the system. Now, the global stiffness matrix times the all degrees of freedom present in the structure, which is d1 to dn, or you can call it as u1, v1, u2, v2, through on to u5, v5, is equals to f, is your equilibrium equation. But you know that this structure is not stable because they are not been uh, taken care to arrest the rigid body motion. That means first you need to arrest so that this structure doesn't move, translate simply in the x direction, y direction, or just rotate about a hinge or about a pin. So for that you need to constrain it enough. So what are the 3 types of rigid body motions we see? That is translation in the x direction, translation in the y direction, and the rotation about any pin joint. To arrest that, our problem had a pin support at the left end and a roller support at the right end. The left end pin support makes it u1 is equals to 0 and v1 equals to 0, and the roller support at the right end makes v3 is equals to 0. Let me show the picture once again. So here my x is constrained, so u1 is equals to 0. My y is constrained, so my v1 is equals to 0. Here, since it is on the roller, it can move along x direction, but it cannot move along the vertical direction. So v3 is equals to 0, not the u3. So if I put all these 3 into the picture, then I will be able to solve this problem. Now this structure, now I impose those things by making it only the unknown degrees of freedom. The unknown degrees of freedom are u2, v2, u3, u4, v4, u5, and v5, which I call it as uu. Correspondingly, I need to get my kuu. How I get my kuu? I need to eliminate the rows and column entries coming from the rigid body. It's very simple. So corresponding to whatever has been constrained, you remove them or you cross them. So the corresponding to u1 I have removed it, corresponding to v1 I have removed it, corresponding to v3 I have removed the row. Similarly, I need to remove the column. Anything that entries remain which are not crossing them, and if that nothing is there, you have to take a 0 value. For example, here it is a 0 value. Here it is a 0 value, 0 value, 0 value, 0 value, 0 value, 0 value, 0, 0, 0, and this is 0. Correspondingly, you just take that, you will get your KUU. And this KUU represent a constraint stiffness, so this can be invertible. That means KUU inverse exists. However, earlier KG inverse doesn't exist because the rigid body motions are not constrained. So KG inverse doesn't exist, but KUU inverse exists. Since KUU inverse exists, I can bring it to the other side, compute the KUU for the given matrix that we have computed earlier, and we also have the total force field coming onto this FU, which is obtained by just removing the entries from the 1, 2, and 6 degrees of freedom. So this gives me my FU, and I take my FU, get my KUU, and I invert this thing, I'll get my unknown degrees of freedom. That means I'll determine, by doing this inversion and this thing, I'll determine all the things. Now I know all the degrees of freedom. Once you know all the degrees of freedom, when you multiply it, the reaction forces are corresponding to the first, second, and sixth entries, because those are the known displacement field at the, or the constraint fields. At the constraints, you will end up with the reaction forces. Those correspond to our reactions. So this is how one could generally compute a truss problem in at in a academic sense. The same thing can be used to write a MATLAB program, which I will describe it at a later point after I finish the beams. So if you have any questions at this point of time, I would stop and I will ask to convey your questions so that I'll try to resolve them to the extent possible. I want to change this one as, instead of taking I as 5 and J as 1, this as I as 5 and J as 1. If you want to take this as 1 and that as 5, the angle, it will not make 120 degrees, because if I take I, this is the angle theta with the horizontal. But if I take this as the angle, because angle is measured with respect to I, anytime you take this thing, the angle is measured with respect to I and to the horizontal. This is theta. So when I take this as I, my angle is measured from here. If you want to take this as I, your angle will be measured from here. So in that case, if I want to take this as 1 and this as 5, this will become plus 60 degrees. Accordingly, your C and S will change. However, your stiffness matrix will look something like this. So let's say, let me cut it. I just pasted it. What I've done is I've taken 5, I as 5 and J as 1. I ended up in this stiffness matrix, but let me call it as new element 5 dash, whose I is 1 and J is 5. In that case, my degree of freedom is U1 V1, U5 V5, U1 V1, U5 V5, U1 V1, U5 V5 would be something like this, and it will come the same thing. So what you need to do is, this 1 and 1 will go here. You try to compute it, it will come to be the same, but I'm promising that it will come. But this exercise, you can do it yourself. With the new angles, you will end up with the same thing as what I'm writing it. So this would be minus, sorry. This is, there was a minus sign missing. I don't know how I missed it earlier. This is a minus sign is there. Fifth element, right? So this, there's a minus sign here. So I don't know how I missed it. But anyway, this would be correct. So because the sum of all these rows has to be equal to 0. So even if you do it in whatever manner you want, I as 5 as j as 1 or this thing, this would be unchanged. It will come in the same manner. It's just like reshuffling it here or in this manner, it will be the same thing, because the stiffness should not depend on the nomenclature. Let's say a character of a person should not change on the name you have given to him, because name is only a nomenclature you are used. Let's say if you have um, uh, a kind of uh, a object or a cell phone or something, just because you call it as an iPhone or a J phone, if it has made up of same material, the properties of it should not change at all, because that is the characteristics of the property, and nomenclature has nothing to do with its behavior. So either you define as this manner or that manner, the stiffness should remain unchanged, but correspondingly the entries will be changed. But if you look at u1 u1 entry, either you come from this one u1 u1 entry, it would be the same, or you come from here, it would be same. Similarly, u5 u v5 or u5 v5 or any those combinations, the combinations would remain same. So that is one thing one has to remember. It's good that students are asking some good questions. So if you have any more questions, please let me know. Points are nothing but nodes. There are only 5 nodes: node 1, node 2, node 3, node 4, node 5. But there are elements that connecting the nodes. So this black member is element 1, which is connecting 1 and 2 node, or 1 and 2 joint. And the element 2 is the joint, the member between the joints 2 and 3. So 4 4 is the element, 5th is the element, 6th is the element, and 7th is the element. Okay, so you want to see what is the theta. So let me just copy this picture and I will try to explain it, how I got my thetas. Okay, so let me just copy it here and I will place it here. Okay, so for the fourth one, this is fourth element. For the fourth element, this is I and this is J. I is what? I is to J. So my theta is this one. So this is 180 degrees. Now let us look at the element phi. Element phi I've taken as I is equals to phi and J is equals to 1. So my angle with respect to horizontal is either I need to take this or I need to take this fellow. So I took this one. So this one is 60 degrees and this one is 60 degrees. So this angle is minus 120 degrees. Now coming to the sixth element I have defined again as I is equals to phi and J is equals to 2. With respect to horizontal, this angle it makes is minus 60 degrees. Because it's an equilateral triangle. This length is L, this length is L, this length is L. So this is 60, this is 60, this is 60, this is also 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 60, and this is also 60. So this angle for the fifth element is minus 20. This 60 minus 60, this minus 60, this makes minus 20. Because I'm going in the clockwise direction, this is since I'm going and measuring in the clockwise direction, it is minus 20, or I can make it as something like 180 plus 60, 240. If I measure in the anti-clockwise direction, I can take it as 240 degrees, and I need to always measure from I to J. Theta is measured from I to J, not J to I. So if you remember that, then your angle measurement remains easier and you will get your correct cosine and sine. This is very important. You are defining any element. If you are defining I to J, you have to measure from the horizontal starting from the I to J. So here also my I is here and J is here. So from the horizontal I need to measure towards the element. So either I can measure in the clockwise manner or the anti-clockwise manner. clockwise will give me negative angles, anti-clockwise will give me positive angles. This is how I've measured that. So this is the second question what people are having some things. So glad that people have asked me this problem. And if you have any element connects U1 V1 and U3 V3. There are two elements that may connect it, but not directly. That means they are unaffected. U1 V1, U3 V3, if that is nothing is there, you need to take a zero value. So here I didn't write it, but you need to take all these entries as zero. Wherever I didn't make any entries, these values are zeros. So anywhere if they're not connected, their entries are unaffected. So by changing one thing, you may not affect the other thing. That means there are no stiffness changes by changing U1, there you will not get stiffness changes at the 3. Or by changing the displacement at 3, you will not get stiffness changes at 1. Or if you want to understand in a physical manner, if you change the displacement at 1, there will be no equilibrium forces required to keep the structure under equilibrium. And similarly, the vice versa. So it's a very important question that you have asked, and I really appreciate for that. So if you have any more questions, feel free to ask me, because in the next class we'll skip this one and we'll go to the we'll